This chapter is called Instructions, Language of the Computer, and this is the part one of that set of presentations. And the reason that it's called Instructions is because we're going to take a deep dive into how do we design an instruction set. And we're going to be using a subset of the ARM ISA, which for the purposes of the book and the purposes of the example, to make the point that is something like the ARM is based on that, but the ARM is a complex machine. So it wouldn't lend itself to a pedagogical use if you take it as is. So they have the still in the book and taking a subset of it, and they call it a leg to this sort of watered down version of the processor. So we're going to take a deep dive of the ISA and how to design that among other components of the overall architecture of a processor. But the reason that the chapter is called Instructions is because the ISA, the instruction set architecture, is the bulk of that architecture of a processor because it represents the abstraction that provides an interface, a constant and reliable interface between the implementation at the whatever level you want to look at it, even at the circuit physical level, and the user. So in this case, the user, the most common user would be a person writing a compiler that is going to translate some high-level language to the actual machine language or assembly language, which is essentially the same thing, two different representations. Assembly being mnemonic-based, the machine being the ones and zeros, but there is a one-to-one correspondence. So this abstraction provides that constant interface to the user. So it's very, very important. Okay. So different processors have different instruction sets, and that is the main differentiator of different processors. And what that means is that if you compile a program for, let's say, a Pentium, is not going to run on an ARM because it's a different instruction set. You have to recompile your high-level code, and that's why high-level code is so attractive, because it's portable. You can just take it to the other machine and recompile, and now you have the new machine code for that other processor. So different processor architectures have different instruction sets. But the aspects are common. We're going to see different approaches to architecting processors, but we're going to end up to the one that is used the most these days, which is a load store type of architecture, also called RISC, for reduced instruction set architecture. And what that really means is that you trade off and provide simplicity so you can implement at a higher speed at the expense of having to use more instructions, because the instructions are simpler. The premise of that is that memory is inexpensive relatively, and you can afford to have larger binary files for the programs because you require more instructions because they do less. So we'll see that as we go through the chapter. So again, as I mentioned, we're going to be looking at a subset of the ARM V8 instruction set. And for the purposes of the book, this is called leg V8. Again, ARM was commercialized by a company that was called ARM Holdings, and they from England, and they no longer actually they were bought out by SoftBank, which is a Japanese conglomerate of companies. So they have not just a large share of the embedded core market, they have the largest share. Mostly every cell phone has an ARM core in it, or a multi-core ARM processor these days. So it's very entrenched, and it's all over the place in different things. So The other thing that makes the ARM attractive is that it's representative and typical of modern ISAs, which is this this RISC type load store architecture that trades off or gets simplicity and holds that as a high priority in the design for the purpose of being able to implement the processor at a high speed and provide overall, even though you require more instructions, you come out ahead from a performance perspective. So these are the things that we're going to be looking. It's very important to understand the terminology. So this is like the language of computer architecture. We're going to be looking at the instructions themselves. And when we talk about instructions here, we're talking about the native, many times atomic at the execution level, instructions of the processor from an assembly or a machine code perspective. These instructions are going to have fields. So the instruction that we're talking about is an actual collection of bits. Okay, it's an actual collection of bits, and that word, that instruction word, is going to have fields, and we're going to be able to see that bits 31 down to 26, those mean something. Okay, or the last 4 significant bits, or the last 7 significant bits, that field means something. So that's the instruction word, and those fields in the instruction, how they get arranged, perhaps in different combinations and different types of fields, are going to give us instruction formats. So we're going to see that we have several instruction formats that are used that represent different types of instructions, they do different things. Hello? Was that a question? No?
No, it's not. I'm sorry.
No, no problem. Okay, so we're going to see that we can package and group different collection of field formats or combinations in different instruction formats that do different things from a functional perspective. Okay? We're also going to be talking about the instruction size. So in the case of the ARM, the instruction size is 32 bits. That's the size of the instruction word. We're going to be talking about opcode or operation code. That's the part of the instruction. That is a field in the instruction that actually tells the processor what that instruction is going to do. So when the instruction gets decoded, so that we're going to see that that's part of one step at the micro level of executing an instruction, the first thing that you have to do is fetch the instruction. You have to get that instruction from memory, because that's what the program is. The program is just a sequential collection of instructions in memory when it gets loaded by the operating system and execution starts. So it starts at the beginning, and then it's just a sequential collection. Now the program can jump around because you have if statements that get translated and for loops, and you have function calls and all that, but it's going to be limited to that program image. Okay? And if we want to get more complex about it, we can say that the image can change dynamically in modern operating and complex operating systems like Windows, because you have dynamic linked libraries, the DLLs. So it can get complex, but let's not get bogged down on that. Let's just say that there is a collection, a space in memory with a collection of instructions, and each instruction, regardless of the instruction format, is going to have a field called opcode, which is going to tell the processor what it needs to do when the processor decodes the instruction, which is the next step after fetching the instruction from memory. So you fetch the instruction from memory, and now you decode it by the hardware in the processor, by the logic, and then you use that information to manage the data path, which is what transforms the data. So you start seeing now what is really happening at the hardware level by the logic, by all those logic gates, those millions of logic gates that we studied in ENG 312. Collectively, that's the instruction set. All the instructions that this machine runs. And when you augment that instruction set with other aspects, how the memory gets accessed, maybe some how interrupts and exceptions get handled. When you augment that instruction set with all those other aspects, you end up having the instruction set architecture definition of the processor that defines that processor for the user, that compiler, that person writing the compiler. So we're going to get there for the leg version of the ARM that we're going to study in this chapter. And before that, we're going to take a tour through several types of architectures, which are a bridge to the actual implementation. But it's mostly architecture because it defines the resources and how those resources are organized later on in the implementation for the user. So we're going to look, for example, at a stack architecture, accumulator architectures, and general purpose register architecture, which is the one that the ARM falls under. It is a type of architecture that works on registers, on a data structure, a hardware data structure, which is a register file, which is just a collection of registers. Okay. And the ARM has 32 of those registers to work with that are visible to the programmer. That's the other thing. Everything that in the instruction set architecture is visible to the user. There may be a lot of other components and hardware that are not visible. That's not part of the ISA. That's part of the implementation. Okay? So again, the instructions, those are what's in memory, okay? And they are in machine languages. They are ones and zeros. Each instruction, just to summarize these definitions, have the fields that provide the details of the control. And then the instruction format are the different ways that different fields are laid out in the instruction, within the instruction, to provide that control. Then the instruction size is the number of, you can say bytes or bits, but essentially, what is the uniform size in reality, in actual bits of this instruction? And of course, you can translate that to bytes because they are usually, not always, a multiple of 8 bits. So you can say, we have so many bytes of in the instruction side, but there are processors that are 18 bits for the instruction. So that's not a multiple of a byte, or 22. So let's keep going then. So we talked about the opcode. This is the actual operation, the actual field that tells the hardware what the instruction is supposed to do and how it manages the data path after it gets decoded. All right, so I said that these instructions are in memory. So when the operating system loads the program, so when you double click on a program and it runs, what the operating system does is it reads the binary from the disk and loads it in memory, okay? And loads it in memory. And then it vectors to the start of the program. So you run the program at a simplified level. Normally, this code in in systems that are modern, that have an operating system, this code is what is called relocatable, meaning that the address of the different instructions in the program are relative to some vector that is the start of the program. And the operating system will manage the actual vector, but the addresses of the instructions within the program, if you have to jump to a specific instruction from another, that's going to be relative, because you don't know where the operating system is going to put the program when you compile it. So that's called relocatable code. It applies to code that runs on top of an operating system, and the operating system manages the actual location. But many embedded systems that don't employ an operating system, the actual addresses of the program are physical locations that are fixed in memory. Okay? So we're going to, as I said, we're going to look at several just for, so you can see the difference of different ways of architecting and organizing a processor. So we're going to look at a stack architecture. Okay. So a stack architecture uses 0 operands. So that's the other part. Those are the other fields. So we have the opcode. Some of the other fields may be the operands. What are the operands? The operand fields specify what is the data. What is the data that the opcode is going to operate on? So that's a type of field, the operands. The stack architecture takes 0 operands because it's always implied that you're operating on operands that are at the top of the stack, and we'll see that. Then we're going to look at an accumulator architecture. So one of the operand is always implied to be that accumulator. Therefore, you only have one operand. So normally you need at least 2 operands to do something useful. Normally, you could have an instruction that does something on a single operand. But let's say you're adding 2 numbers, so you have 2 operands. The accumulator architecture always assumes that one of the operands is the accumulator, so it has one other operand specified in the instruction. And then the general purpose register architecture that we're going to be looking in detail throughout the chapter, you specify all the operands. Okay? So we're going to see that. By the way, in the lab, one of your labs is going to do, one of your labs, and one of the most challenging labs is one where you actually get to design an accumulator architecture processor, which is a toy processor that I put together. So it's not, you won't be able to find it online or anything like that. And you're going to have to actually code it in Verilog completely and simulate it and make sure that it works. And that's one of the labs that is coming down the pike here in the lab. So we're going to take a look at these different approaches. So as an example of different machines, we can see these machines that these are just model numbers, okay? Like B5500. So that was a stack architecture. An older type of processor, PDP-8, that was very, 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 very popular in the 1970s, early 80s, late 80s, even, was the PDP-8, which was an accumulator. And then another very higher end type of computers, the VAX line and the IBM 360 mainframe was a register, sort of more genetic register and memory type of approach. So that's a historical view there. These days, processors are really a register type implementation. So how would a stack what type of instruction a stack architecture would have? Okay, so if you had a stack type of machine and you wanted to add two numbers, you would have an instruction that says push A. That's your operand, but push A means move A, whatever that data is, from memory to the top of the stack. So the stack is a well-defined data structure, hardware data structure, different from a register file. You basically always read and write to the top and move the pointer and update the pointer. Then you would push B, your second operand, to the stack, and then the next instruction would be add. And that would automatically add the two pieces of data at the top of the stack. And then the result would be at the top of the stack. And then you would say pop C. And you would place the top of the stack in a memory location. A, B, and C are symbolic memory locations. For an accumulator-based approach, you would say load A, and that would move whatever is in address A to the accumulator. And then you would say add B. So that would add the contents of the accumulator with whatever is in address B and put the results in the accumulator. And then you would say a store C, and that would move the contents of the accumulator to memory address C. For a register memory type of approach, you could say load register 1 with what is in address A, then add the contents of register 1, whatever is in address B, and put the results in register 3, and then store what is in register 3 to address C. And finally, what we're going to see, the simplest type of approach, which is a register file. Think of a register file as a scratchpad of registers. You should know what a register is. At a hardware level, it's a collection of flip-flops. This is really what we're talking about, real hardware. So since you can only operate on registers, you would load register 1 with what is in address A. Then you load what is in register in address B to register 2. Then you would add the contents of register 2 and register 1 and put the result in register 3. And then you would store the contents of register 3 in address C. All these sequences of instructions have the same results. It basically ends up with the sum of the contents of memory locations A and B in memory location C. Well, you can see that there is different ways of approaching it. Okay, there are certain benefits in simplicity on the stack approach, although there are some limitations. But you can certainly see, if you put the stack approach aside, that the register load store approach that only operates in registers, and the only interface between memory and the register file are through loading or storing the register, takes more instructions than the other two. So the question is, why is it that we and the most popular and faster processors use a register load store approach instead of an accumulator or a register memory? Okay, that is because simplicity translates to speed during implementation. So you would be able to implement a register load store architecture approach at a higher speed than, let's say, a register memory or an accumulator. Now let's look at the descriptions that I went through in a graphical way, so you can see sort of a sequence of what's going on. So we have the top of the stack. So here we are pushing A. Now we push B. So now we have A and B on the stack. Now we add, and we put the results on top of the stack. And now we move the top of the stack to memory location C. Okay? Now let's look at the accumulator architecture. So the accumulator is a register, a single register that is implied as one of the operand and also where you put the result of the operation. We're going to move A to the accumulator. We're going to add B. So here we're adding the contents of memory location B to the contents of the accumulator and putting the result in the accumulator. And then we store the contents of the accumulator in memory location C. That's the accumulator approach. Here's the memory register. So the memory register, you also have a register file. Okay? So now we're going to load register 1 with A. So it provides that interface. Now we're going to add the contents of register 1 and the contents of memory location B and put the result in register 3. And then we'll move the contents of register 3 to location C. That's the register memory approach. And finally, the register. Notice there is no interface directly between the memory and the data path, which is the actual, or the ALU in this case. We're going to load register 1 with the contents of A, load register 2 with the contents of memory location B, add register 1 and register 2 and put the results in register 3, and then store the contents of register 3 in memory location C. So hopefully that gives you a better idea of how these different approaches work. Again, the one that we're going to go after and spend time studying is this type of approach because it is the most popular. It's been proven to yield high performance processors, and of course is the one that the subset of the ARM ISA that we're going to be studying utilizes. We could also have a memory architecture that has no registers. You could also envision that. This is also called a data flow or a move architecture. And everything is specified as a move from a memory location to another one. So here, you would just say add the contents of memory location A and B and put the results in C. Why don't we use something like that? Well, memory interfacing is slow. That's the reason. And we're going to see as we implement things with techniques like pipelining, while we are loading a register, we could actually be doing some other work on another set of registers. And the compiler would be smart enough through our information and the ISA abstraction that we provide, the compiler would be smart enough to use different registers to allow for that flexibility and that overlap of work to take place, which at the end results in higher throughput of instruction completions and therefore higher performance. All right, so let's look at the type of arithmetic instructions. So this would be a group of instructions that are going to use a specific instruction format. So we see that specific to the ISA that we're going to be studying, these instructions are going to have two sources and one destination, three operands. Whether it's a source or a destination is still an operand, but we have two sources and one destination. A is the destination, B and C are the sources. We're going to see that the leg or the arm, the subset of that arm ISA, all arithmetic operations have this form, meaning all arithmetic operations use this instruction format. We're going to call this an instruction format. You're going to know it as the R format or the register format, but that's just a name in the ISA. The point is to remember that all arithmetic operations take this format. Why do we want to group instructions into clusters or types that have the same format? Well, a very important design principle is not only simplicity, but also regularity. Regularity makes hardware implementation simpler, okay? And simplicity enables higher performance at a lower cost. What is a lower cost in this case? Fewer gates, simpler hardware. What is higher performance? Higher speed. That's what we're after. Higher frequency. So how would we, so you start, you can start taking a look at how high-level statements would get actually compiled into assembly language for the ARM subset. So all this, when it says compiled code, those are assembly language instructions. And once we know the specific format of the instruction and the values that we need to give to the different fields, we're going to see that each of those lines of assembly language can be translated into a binary word of ones and zeros. So let's say that in C, we have this statement where we want to get the difference of two sums, G plus H minus I plus J. So the compiler could come up with code like this. It could actually add H and G and put in register T0. The assumption here, okay, the assumption here is that G and H have been preloaded in some register of the register file. And we're going to see what the names of the registers are, but this assumes that G and H are already associated with the register by the compiler and already loaded to the load instructions. And then it could add H and I and J and put it in register T1, and again they are associated with preloaded registers. And then subtract T1 from T0 and put the resulting F. And again, F is associated with a register. So to make it to memory, I would have to do then a store instruction and put the contents of register F, in this case, that's still an abstraction, into that memory location. So if you get to use the ARM or the Lex simulator, just the double slash is just comments. That's just a comment itself. So when you write assembly language, you have one instruction per line, okay? Because it really translates to a single binary word as it is in memory for the compiled program, okay? So in this case, each arithmetic instruction, we said that they all follow the same format. Therefore, they all have three operands. Okay, they all have three operands, two sources and one destination. Now let's look at this register file. It's 32 registers, okay? 32 registers. And they are X0, they are labeled X0 through X30. And there is a special register, XZR, which it doesn't really exist. It doesn't really exist as a real register, but it's an abstraction that in the hardware gets provided as the value 0. It's always equal to 0, and you cannot write it, but you can read it and use 0. Well, 0 is a very useful number when you're doing a number of things. So as part of the ISA, the architects included this amenity in the ISA. You have the constant 0 there always to be used. You don't have to move it from memory or fabricate it. You have it there. So that's something that they have found through their studies when they were doing the architecture, that was a good thing to have, that in the end it was going to add and increase the performance of the system. Another part of the ISA is the addressable space of the processor. So in this case, the ARM has 62 bits in the memory bus. Okay? So 62 bits, not 64. So it's not it is not a multiple of a byte. So it is 62 bits. Okay? And that is a big number. So that is a large number. Now, the other thing is that the memory address, and this is part of the ISA specification, how the memory gets addressed. So we are addressing with 62 bits, but we are addressing bytes. So the memory is recognized as an array of bytes, and words are going to take a number of bytes. So addresses for bytes are going to be consecutive and differentiated by 1, but words, since they are multiple bytes, they are going to be jumping over every other number of bytes that makes up the word. And we're going to see that later, okay? Now let's look at the collection of instructions of this subset. So we have the arithmetic instructions. So you can see there, we have add, we have subtract, we have add immediate. So let me go through each one of them in more detail. So this one has 3 registers as operands. So register 3 in this case and 2 go into register 1, the addition. This one, register 2 minus register 3, goes into register 1 here. Then we have an add immediate that has 3 operands, but only 2 of them are registers. There is a field there is a field that is an immediate constant. And what that's going to mean is that the constant is embedded in the address itself. Is a field in the, in the instruction. So you should start suspecting that the immediate instruction and the register instruction are two different formats, and we're going to see that. We also have subtract immediate, where we subtract an immediate 20-bit value. I'm sorry, not 20-bit, but an immediate value from register 2, and or the contents of register 2, and put the results in register X1. We have the add S, which is same thing. We're adding these two registers and put it in this register over here, but also we're setting flags. That's part of the instruction set architecture. How do you provide status? Well, the ARM provides it with flags, what is called a special register that is also visible to the programmer that has flags. Flags are 1-bit values that get set or reset. Set means equals a 1, reset means equals to a 0, and they indicate to the programmer certain things about the result of the operation. For example, you could have a flag that gets set if the result is 0, or a flag that is set if the result is negative, or a flag that is set if there was an overflow, or a flag that gets set if the processor ran into some other problem. So that provides information to the programmer so that they can actually handle it and take action. Okay? And hey, if they cannot figure a graceful way to handle it, you get a blue screen and your computer crashes, right? All right, so here we have add immediate with flags, subtract immediate with flags. So these are the subset of arithmetic instructions. In the lab, we're going to take an actual subset of this subset, just a handful of instructions, and one of the labs is for you to design this processor, the leg. So that's also a challenging lab that is coming your way later on. So when I say design it, it means you're going to code it in Verilog and simulate it and show me that it works. So we'll talk some more about that later on. So here we have data transfer instructions. So load register. This is the format. It has 3 fields and 3 operands. Okay. And the way that it works is later on we're going to talk about addressing modes, and that is how you get to the actual operand. There are different ways of doing that. Okay, you can get to it directly from a register. We saw that in here in some of these instructions. You can get to it from an immediate value. We saw that. We can get some type of relative addressing. So this is using that type of relative addressing where we are loading register X1 with the contents of a memory location. But that memory location is equal to the contents of register X2 plus an immediate value, which is a displacement. I guess that you could look at one as the datum and the other one as a displacement, depending on how it gets coded. But the point is that the sum of the contents of the register and an immediate value is the actual address. And then the contents of that memory location is going to register 1. LDUR stands for load unsigned register. That's the other way to look at the contents of memory. How do you define how you view the contents of that memory or the contents of a register, for that matter, But overall, that collection of bits, you could look at it as an unsigned number, or you could look at it as a signed number. The processor doesn't know the difference. For the processor, it's just a collection of bits in memory or in a register. What gives it meaning is you, the programmer. How do we do that in C++? Well, we have data declarations. That's how the compiler knows how to tell the processor how to interpret these numbers. We could declare an unsigned integer, or we could declare a signed integer. So that's why those declarations are there, and that's why they are so important. So in this case, the this load is unsigned, and this is a store unsigned. What does it really mean furthermore in hardware is that if you are storing or loading something that is unsigned, well, you don't do sign extension. We're going to see that because the data path of the ARM is 64 bits, and if you're getting 32 bits, for example, and translate it to a higher number of bits, what you do with that signed bit, with the most significant bit, is depending on how you look at that data, how you are interpreting the data. If it's unsigned, then you just fill with zeros, the upper part of the word. But if it's signed, you have to extend the signed bit. That's why it's important. So here we have load sign word. So again, same type of addressing mode, combining a register and an immediate value. But here we are loading a signed word. And again, a signed word means something for the processor. Okay? Storing a word, loading a half, which is a half word, so half the number of bytes of a word, storing half a word, and then loading and storing a byte. So remember that the way that the data is stored in memory is byte addressable. We can get to each byte individually, and they could be part of a complex data structure that is combined. That's what unions are, right? In C++. So you can look at the same collection of bits in memory as, let's say, an array of bytes, or you can look at it as an integer that has 4 bytes. Here we have a couple of other instructions. The load exclusive register. So part of atomic instructions are instructions that ensure that nothing else is happening during their execution. So you can rely and use it for multiprocessing functions and implement handshake type of protocols, things like semaphores and things like that, just to provide handshake and concurrency and coordination. So those are atomic instructions. Move wide with 0. So this does this, and it's also doing a shift. So move wide with 0. So this register takes the number 20, and then you get a shift, which is this multiplication by a power of 2. So you can shift 16 bits, or shift 32 bits, or shift 48 bits. And then move wide with keep would also it loads 16-bit constant in this case, but doesn't change anything. Okay. All right. So now you got sort of a crash exposure to the subset of the ARM, this instruction set. So let's unpack that a little bit more. We saw the arithmetic instructions. They use register operands. The registers are in this register file. The data path width, okay? The data path width is 64 bits in the ARM. So the ARM, the register file, it has 32 registers, which are 64-bit each. And when it goes through the ALU, and the ALU operates on the registers, because that's where it operates on, the ALU has to be 64 bits wide. From an architecture perspective, this 64 bits is called a double word. Okay? It's called a double word. So we have this 32, or 31, because we have 0, right? That is just there. We also have 32 bits of data structure, and that's what we call a word. So a double word is 8 bytes. A word is 32 bits or 4 bytes. That register file, the ISA allows the user to refer to them as a subset of 32-bit registers, which are labeled W0 through W30. The double word ones are X0 to X30, and that naming convention is understood by the assembler, let's say, which is one level down from a compiler. Although these days, where it's called cross compilers, they do the whole thing. But if you had a program that you wrote assembly language and you wrote these letters, the W's and the adds and all that, machine, you wrote this assembly language that you can read in this mnemonics, you could have a program that simply, as a lookup table exercise, just translates those instructions to the ones and zeros. That's called an assembler. So by convention, we use the X and the W, and the assembler or the compiler knows what to do. Why use registers? Why use a register file? In this case, 32. And why 32 for that matter? Well, architects do a lot of studies looking at the performance and benchmarking the techniques that we discussed in chapter 1 to see what is a good number of registers. Why not 64 or 128 or 256? More is better, right? But what is a good trade-off of performance versus cost? Registers are expensive. So they agreed that 32 was a good number for the application for what they were trying to do. So you want to keep the register file as small as possible while getting the performance that you want. But certainly a register file is much smaller than memory. In this case, memory is the memory that is immediately attached to the processor. In chapter 5, we're going to see that we're talking about the cache, which is made of a specific memory technology called SRAM, which is much faster than DRAM, but also because it's larger than a register file, although the technology is very similar, because it's larger, it's going to be slower. So design principle number 2, smaller is faster. Smaller is faster. Why is that? That should resonate with you, because remember that at some level of abstraction, we are talking about hardware, but it's hardware nonetheless. We're talking about transistors. We're talking about interconnect that have real capacitances, real resistances. And where does the delay come from? Well, the delay comes from, in the interconnect, comes from RC delays. And it really, at these speeds, you can also argue that it comes from transmission line light delays and all different other issues like reflection and things like that. And also from the actual turn on time of the the transistors, and turn off time. These are node capacitance that are being charged and discharged, such as the gate capacitance of a MOSFET. So all this comes from real physical electrical issues, because at the end of the day, all this is implemented with transistors and metal interconnect. Now the ISA further specifies subsets of the registers in the register files for specific purposes. This is just a convention. Why do you want to provide this guidance? And the convention is so that everybody that is utilizing this processor, writing an assembler or a compiler, they're following the same rules. So the guidance is that registers X0 through X7 are used for procedure, arguments, and results. So when you make a function call, let's say in C++, you pass the arguments and get the results through registers that are in the X0, X7 space. Okay? They have specified X8 as an indirect result location register, which means that that register has the address of where the result is. Then you have 7 temporary registers, X9 through X15, and you also have X16 and X17, which could be used by a linker as a scratch register. So that's part of getting a program together. If you have different files and parts of a program that you are compiling or assembling together, before you come up with an overall program, these object modules, as they are called, need to be linked together. That's also done by another software development tool called a linker. So that can be used by the linker. They have specified X18 as a platform register. So it could be a temporary register, but it's there as some type of a specific register for some type of platform. What is a platform? Well, if I'm designing a chip for a cell phone that uses an ARM core, well, that's the platform. It's that chip, that end product, that application-specific chip. X19 through X27 registers are specified as saved registers. So that is 9 registers that get saved during a procedure call. So there is a convention and a guarantee that these registers are going to be saved when there is a procedure call, which is a function call at the assembly level. It would be a subroutine call. So the contents of these registers get saved. We'll see that there is another helper data structure in processors called the stack, which is really in memory. And when code gets compiled and function calls get made, the contents of these registers get saved. And when you return from that function call, they get restored. That way, the callee procedure, so the procedure that you are executing, that subroutine, can use these registers freely, knowing that for sure the original contents are not being overwritten. So they get saved in the stack, they get pushed, and they get restored, they get popped. The ISA also specifies x28 as the stack pointer. Okay, the stack pointer. So again, we saw how the stack works. So you always have to have the address of the top of the stack, and depending on whether you have a pre or post the stack, the top of the stack may be the next available instruction, location, or it could be the one that was used last, and you have to pre-update before you use it. If it's the one that is available, that means that you did a post update when you used it. So that's the pre versus post implementation, which is an implementation detail. Then the register 29 is the frame pointer. So this is only useful for implementing operating systems and operating system level memory management parts of the operating system. And then X30 is designated as the link register. The link register is where you store, when you go to a subroutine, you store the address of the next instruction after the calling of that subroutine. So when you go back, you know what is the instruction that you have to execute, and you restore the that address from there. Okay. So these are the elements of the instruction set architecture. It's not just instructions, it's this collection of specifications. We agree that the bulk is the set of instructions, but it's a lot more than that. There are a lot more specifications in the ISA. Did I hear a question? No? All right, let's keep going then. Oh, we missed the zero register. So some contrast of different processors, different ISAs. What we're looking at here, from a register perspective, we have 32 64-bit registers. MIPS, which is another popular ISA, has 32 registers, 32 bits each. The older Motorola 68000 line had 16 32-bit registers. And the Pentium has only 14. That probably surprises you, that something so modern, so powerful, has so little registers. That is because it's a different approach. It's not RISC. The origins of the Pentium is a different approach, more like a memory register type approach, and is what was referred to as a CISC, not a RISC. A CISC, which stands for Complex Instruction Set computer or processor, and the instructions were at the beginning they were complex instructions. At some point, they realized that was hindering the speed, and they actually added things that are of a RISC nature, but keeping the old CISC baggage, because it was important for Intel to make sure that any compiled code that was ever written still ran on any Pentium or Intel processor. But RISC refers to as much as you can registers, and that's what you work with, and simplicity in the instructions. Okay, so the compiler knows, and you could actually take a course on compiler design, and there are a lot of techniques on how to do this and a lot of algorithms to optimize the usage of the registers. But if we want to increase the performance, we want to keep things in the registers as long as possible. Okay? Because if we have to go out to memory, that's going to take longer than accessing the register file. Why is that? Because memory is bigger than the register file. Although the technology may be very similar, but the actual size, the physical size, those longer wires have capacitance and resistance, and that makes it slower. Also higher power. Okay? So I think we saw this example in, again, you can be, the compiler may have associated the variables F, G, H, I, and J with a number of registers. So, then you would add G and H. So G and H would be in this two. Then you would add I and J associated with these registers. And then you would do the subtraction. And X19 would be the one associated with F. So let's talk about memory operands. So everything is in memory. At some point, and memory is a unified structure, and it gets complex because of the number of cache and whether the data and the code are split and at what point. But at some point, from a programmer's perspective, memory is a single data structure that has everything. The operating system manages the details. But in a load store architecture, we have to get things from memory into the register file because we only operate on the register file. Okay? And as I mentioned, memory is byte addressable. The actual address is the address of a byte. But depending on the instruction, as you saw, if you load half word or if you load a byte, the hardware knows, according to that instruction, how to handle that data transfer. If you have an instruction that is loading a byte from that address, it's going to load just the byte at that address. But if the instruction is loading a half word that is 2 bytes, it's going to load the byte at that address and the one next. Okay? The other thing is, as part of the ISA, is that the data does not require the words to be aligned at the memory or word boundaries. So remember that a word is 8 bytes. So word 1 would be at byte address 0. And word 2, well, word 0, let's start counting everything at 0. Word 0 would be or would start at byte address 0. Word 1 would start at byte address 8 because it's every 8 bytes. Word 2 would be at byte address 16. What we're saying is that the words don't have to be aligned. Let's say that you stored just a byte at address byte 0, and now you wanted to store a word, you could store those eight bytes starting at byte 1. You don't have to basically store it at byte 8 and waste 7 bytes of space. That's a very efficient way of doing it. Okay? So let's see if we can show you some graphical examples. So let's say that a word, in this case, is 4 bytes. And let's say that a byte we know is a constant of 8 bits. Here, the addresses would be byte addresses, 0 all the way to 7 in this case. And then word 0 would be these 4 bytes. And word 1 would be this next 4 bytes. And going back to the previous slide, what we're saying is that if I just store a byte, and that is a byte here, this word 0 could start at byte 1. I don't have to align it with a word address, because the word addresses are every 4 bytes, because I have defined a word to be 4 bytes. So it would be, in this case, 0, 4, 8, 12, 16, and so on. The reason we provide this byte addressing is that bytes are useful. Text is coded as bytes. A lot of information is text. So it would be very wasteful to force a minimum data structure that would be a higher number of bytes than 1, because a lot of information is just 1 byte. Now there are 2 ways of storing the bytes of data that requires a multiple number of bytes in memory. Okay? The first one is what is called big endian. And the processor is actually an arbitrary decision. They have been, it's actually a great paper that I usually assign students to read. It's a classic, very old paper that explores the benefits of what is called Endianism, and in a sort of humorous way, and but very, very thought-provoking. Even to this day, is a good read. But it's really arbitrary. A lot of modern processors, actually, you can select, and the operating system selects this, how the multi-byte data is going to be stored in memory, i.e., the operating system can select the endianism that the processor is going to use. Okay? So what we're referring to is that when you have a data structure that takes a multiple number of bytes, let's say that in this case, I have a word and each word is 8 bytes. Then the question is, do I store first the most significant byte of the word or the least significant byte? That's what endianism is. So we have big endian, which means that in this case the leftmost byte is the word address. So we would essentially store the most significant byte as the last address. So we first store the most significant byte in memory. So this is memory address, let's say 0. And this is memory address 1, 2, and 3, and so on. But this is the, I'm sorry, we're here. The big Indian type, the leftmost byte is the address. So we would store the most significant byte at this address and go down that way. Little endian is just the reverse. The rightmost byte is the word address, okay? And we store it the other way. So that's just how multi-byte data structures get stored in memory, because you have to choose a way. And again, it's just arbitrary, but you should know that that distinction exists. So in this case, we have words that are 32 bits, so 4 bytes, and double words that are 64 bits. So each double word is comprised of 2 words. But again, the memory array, and the most important thing to keep in mind is the addressing in memory is 1 byte at a time. This is going to become important because when we try to access data that is multiple bytes in length, like let's say an integer that tends to be 4 bytes, this would be, and if you have stored an array of integers, this would be the 0 member of that array, and this would be the number 1 member of that array. But from a memory perspective, the addresses are 0, 1, 2, 3. So if you want to access this member of the array, you have to shift your initial pointer to the array by 4 in this case. So we'll see some examples of that coming up. And this is a very specific example of endianism. So here we see that with big endian, the most significant byte, which is 98 in this case, gets stored first. That's all it means, because these are all bytes. Now, the bits in the bytes are always going to go from most significant on the left to least significant on the right. There is no question there. It's just how you store these multiple bytes for this 4-byte data. Okay, so this would be 32 bits. So the most significant byte on the left gets stored at the lowest address, and then you go up. That's for big endian. For little endian, the least significant bit, so here would be a CD, would be here. The least significant byte is the one that gets stored at the lowest address. Okay?